In the remote heart of Siberia, on a quiet summer morning, an unprecedented event unfolded. Far from the bustling cities of the world, an invisible force descended upon Earth, unleashing a destructive power unlike anything witnessed in modern history. It was June 30, 1908, and the dense, uninhabited taiga forest was about to become the epicenter of a mystery that would baffle scientists for over a century. A force unseen, unheard by most, yet its impact resonated globally, hinting at the vast, untamed cosmos beyond our atmosphere. This was the Tunguska Event, a name now synonymous with an enduring scientific puzzle. The local time was approximately 7:17 a.m. For the nomadic Evenki people, tending their reindeer herds in the vast expanses of the taiga, it began as an ordinary day. The air was cool, the forest alive with the sounds of nature, a tranquility deeply ingrained in the ancient rhythms of this land. But this serenity was about to be shattered by an event so sudden and profound that it would forever alter their landscape and their oral traditions. Imagine the quiet anticipation of dawn, the deep green canopy of ancient trees, and the solitude of a world far removed from human civilization, utterly unaware of the cosmic collision fast approaching. Without warning, the sky erupted. Witnesses, many kilometers away, reported seeing a blinding flash of light, an intensely bright object streaking across the heavens. It moved from southeast to northwest, a fiery projectile illuminating the morning sky with an unnatural brilliance. The initial visual was quickly followed by an unsettling cacophony, rushing winds, a deafening roar, and then a series of thunderous explosions that seemed to tear through the very fabric of the air. This was no ordinary meteor shower. This was something far grander, far more terrifying, signaling an event of immense power unfolding high above the unsuspecting Earth. What followed was an airburst of unimaginable magnitude. The object detonated not on the ground, but several kilometers above the surface, releasing an explosive energy estimated to be equivalent to 10 to 15 megatons of TNT. This was hundreds of times more powerful than the atomic bomb dropped on Hiroshima. The resulting shockwave, a colossal wave of compressed air, flattened an area of dense forest exceeding 2,000 square kilometers, obliterating some 80 million trees. It was a terrifying display of raw power, a stark reminder of the cosmic forces that can, at any moment, reshape our planet's surface. While the immediate devastation was confined to the remote taiga, the event's repercussions echoed far beyond. Seismic monitoring stations across Europe detected significant tremors, registering the equivalent of a 5.0 magnitude earthquake. Barometric instruments as far away as Great Britain recorded sharp fluctuations in atmospheric pressure, indicating powerful pressure waves propagating across the globe. This was a clear sign that the Tunguska event was not just a local phenomenon but a planet-scale occurrence, a cosmic punch delivered with such force that its vibrations literally rippled through the Earth and its atmosphere, alerting a nascent global scientific network to its presence. For several nights following the Tunguska explosion, an eerie and beautiful phenomenon captivated observers across Europe, extending even to parts of the United States. Skies that should have been dark remained unusually bright, glowing with an otherworldly luminescence. This bright night's effect was caused by sunlight scattered from vast amounts of fine dust and ice particles, propelled high into the upper atmosphere by the immense blast. These particles, reflecting sunlight from beyond the horizon, created what are now recognized as noctilucent clouds, an ethereal spectacle that inadvertently provided the first distant clues to the true scale of the Siberian event, painting the night with an unexplained brilliance. Despite its global atmospheric signature, the Tunguska event occurred in one of the most inaccessible regions on Earth, the Central Siberian Plateau. Vast, rugged, and almost entirely devoid of roads or infrastructure, the blast zone was thousands of kilometers from any major settlement. The nearest indigenous communities, primarily Evenki and Yakut, lived a subsistence lifestyle, isolated from the wider world. Their initial accounts, often tinged with fear and ancient superstitions, spoke of heavenly fire or a sky god's wrath. It would be years, even decades, before the outside world could properly investigate, leaving the immediate aftermath to the whispers of legend and the slow, inexorable forces of nature. The early 20th century was a turbulent time for Russia and the world. Tensions were mounting across Europe, soon to erupt into the First World War. Russia itself was on the brink of profound internal upheaval, culminating in the 1917 revolution. News of a strange explosion in a distant, unpopulated corner of Siberia was, understandably, not a priority. Reports were fragmented, often dismissed as folklore or exaggerations, struggling to penetrate the cacophony of global political crises and impending conflicts. The world had bigger concerns than a remote cosmic mystery, and thus, the Tunguska event faded into obscurity for years, waiting for a quieter moment to demand attention. Despite the remoteness, accounts from those who experienced the event firsthand paint a vivid, if terrifying, picture. One eyewitness, Semenov, a local farmer, described the sky splitting in two, with fire appearing high over the forest. Others spoke of a pillar of fire, deafening thunder, and a searing heat that scorched their clothes and left them dizzy. Reindeer herds were annihilated, homes flattened, and people were thrown off their feet, some rendered unconscious. These raw, unfiltered testimonies, collected years later, provided the first human connection to the immense power unleashed that morning, a testament to its profound and terrifying impact on those nearby. It wasn't until the 1920s that a dedicated scientific effort began to unravel the Tunguska mystery, led by Soviet mineralogist Leonid Kulik. Driven by an insatiable curiosity and a deep scientific rigor, Kulik became obsessed with finding the impact site. His initial investigations in 1921 confirmed the widespread local stories, solidifying the need for a full-scale expedition. Kulik's dedication was singular. He saw Tunguska not just as a local anomaly, but as a critical piece of Earth's cosmic story, understanding its scientific importance long before it was widely recognized. His pioneering work laid the foundation for all subsequent research. Kulik's initial reconnaissance in 1921, though brief, was crucial. Facing immense logistical challenges, including the vast distances, unforgiving terrain, and limited funding in post-revolutionary Russia, he managed to gather first-hand accounts from local Evenki survivors. These stories, combined with observations of unusual soil and atmospheric phenomena, convinced him that a major meteorite impact had occurred. This preliminary journey, often overlooked by the dramatic later expeditions, was the intellectual spark that ignited the serious scientific pursuit of Tunguska, transforming it from a local legend into a global scientific enigma worthy of rigorous investigation. It set the stage for decades of arduous work. Between 1927 and 1939, Kulik led 4 major expeditions deep into the Tunguska region, enduring incredible hardships. His primary goal was clear: to find the impact crater, the definitive proof of a meteorite strike. He navigated treacherous swamps, battled swarms of mosquitoes, and endured the extreme Siberian climate, all while meticulously mapping the devastation. These expeditions were monumental feats of endurance and scientific dedication, pushing the boundaries of exploration in an era before modern transport and communication. Kulik's relentless pursuit of the crater became synonymous with the Tunguska mystery itself, a testament to his unwavering scientific resolve. Upon finally reaching the blast zone, Kulik and his team were confronted with an awe-inspiring scene of devastation. An area spanning over 2,000 square kilometers, larger than many European cities, lay utterly flattened. Millions of trees, primarily Siberian larch and pine, were felled and scorched. What struck Kulik most was the radial pattern of the fallen trees. They all lay pointing away from a central point, an invisible epicenter. This unique butterfly pattern strongly suggested an explosion originating from above, a powerful airburst that radiated its destructive force outwards, leaving an indelible scar on the ancient taiga landscape, a silent monument to its immense power. Despite the overwhelming evidence of an enormous explosion, Kulik faced his biggest puzzle: there was no impact crater. According to prevailing scientific understanding, a meteorite of such destructive power should have left a massive, unmistakable hole in the ground. Yet, after years of meticulous searching, digging, and mapping, Kulik found nothing more than shallow, marshy depressions, inconsistent with a direct impact. This crucial absence of a crater would become the defining enigma of the Tunguska event, challenging conventional meteorite theories and opening the door to more unconventional explanations for the cosmic visitor's ultimate fate. Convinced that the crater must exist, Kulik focused much of his later efforts on a large, roughly circular marsh near the center of the radial treefall, known today as the Southern Swamp. He theorized that a meteorite might have fragmented and struck there, or that the soft ground had absorbed the impact. He even attempted to drain the marsh in a desperate effort to reveal what lay beneath. However, drilling and further geological studies eventually revealed that the swamp was a natural formation, its depths filled with peat and sediment, not the fragments of an extraterrestrial body. It was a painstaking and ultimately disappointing false lead in his quest. Decades after Kulik's initial expeditions, advanced scientific techniques yielded new clues. In the 1950s and beyond, researchers discovered microscopic magnetic and silicate spherules embedded in the soil and trapped in the resin of surviving trees from the blast zone. These tiny metallic and stony beads, typically only a few tens of micrometers in diameter, bear chemical compositions distinct from terrestrial origins, strongly suggesting an extraterrestrial source. While not large fragments, these microspherules provide compelling evidence that an object from space did indeed impact Earth's atmosphere, leaving behind its dust as a cosmic signature, a silent whisper of its passing. In the decades following the event, particularly after the advent of the nuclear age, some theories emerged suggesting the Tunguska event might have involved radiation or even a miniature nuclear explosion. Claims of mutated plants and animals in the blast zone fueled these sensational ideas. However, extensive scientific investigations, including detailed analysis of tree rings and soil samples, have consistently found no evidence of elevated radiation levels attributable to the event. The observed biological anomalies were later explained by natural postfire forest regeneration and genetic mutations not linked to radiation, decisively discrediting these initial, more speculative, hypotheses. Science eventually prevailed over speculation. Today, the most widely accepted scientific explanation for the Tunguska event is the airburst hypothesis. This theory posits that the celestial object, rather than striking the ground, exploded several kilometers above the Earth's surface. This atmospheric detonation would generate an immense shockwave, capable of flattening trees in a radial pattern without forming an impact crater. The intense heat and pressure from the airburst would also vaporize most of the object, explaining the lack of large fragments. This elegant solution reconciles the observed devastation with the puzzling absence of a crater, becoming the leading contender in unraveling the century-old mystery. For many years, the most straightforward explanation was that a stony or iron meteorite caused the event. Meteorites are the most common extraterrestrial objects to impact Earth. A large stony or iron meteor, exploding in an airburst, could certainly generate the observed energy and shockwave. However, a key challenge remains. While an airburst would vaporize much of the object, a stony or iron meteorite of that size should still leave behind at least some detectable, larger fragments or traces beyond microscopic spherules. The lingering question is, if it was a meteorite, where are these expected larger pieces, and why have they remained so elusive in the blast zone? An alternative, and increasingly favored, theory suggests the Tunguska object was a small comet. Comets are often described as dirty snowballs, composed primarily of ice, dust, and frozen gases. If such an object, perhaps 60 meters across, entered Earth's atmosphere at high speed, the intense heat and pressure would cause it to rapidly vaporize and disintegrate in a spectacular airburst. This scenario elegantly explains the lack of an impact crater and the absence of any substantial meteoritic fragments, as the icy composition would simply turn to gas and disperse. It's a compelling solution that fits many of the observed anomalies. The concept of a comet as a dirty snowball was popularized by astronomer Fred Whipple in the 1950s. This model describes comets as icy nuclei with embedded dust and rocky material. When such a fragile, low-density object enters a planetary atmosphere at high velocity, the extreme aerodynamic stress and frictional heating can cause it to break apart and completely ablate. Unlike a denser stony meteorite, which might fragment into solid pieces or form a crater, an icy comet would undergo a much more dramatic and complete disintegration. This physical characteristic perfectly aligns with the Tunguska paradox, a massive explosion with no discernible ground remnants. The primary scientific debate boils down to whether Tunguska was caused by a stony meteorite or an icy comet. both have strengths and weaknesses in explaining the event. A meteorite offers a more common type of impactor but struggles to explain the complete lack of fragments. A comet provides an elegant solution for the missing crater and fragments due to its volatile nature, but comet impacts of this size are rarer. The definitive answer remains elusive, yet ongoing research and improved analytical techniques continue to refine our understanding, bringing us closer to identifying the true nature of that mysterious Siberian visitor. The speed at which an object enters Earth's atmosphere plays a critical role in how it behaves. The Tunguska object is estimated to have been traveling at hypersonic velocities, perhaps 15 to 30 kilometers per second. At such extreme speeds, the atmospheric drag creates immense pressure and heat, building up rapidly on the object's leading edge. This intense pressure can cause even robust materials to stress and deform. For a less dense object, like a comet, this velocity ensures a catastrophic airburst. The sheer kinetic energy, amplified by speed, transforms the atmosphere itself into an anvil, crushing and exploding the incoming object before it can ever reach the ground. The airburst phenomenon involves a rapid sequence of events. As the object plunges into denser atmospheric layers, the pressure difference between its front and rear surfaces becomes extreme. This stress causes the object to fragment into smaller pieces, each piece then undergoing its own mini airburst. This cascading disintegration releases energy over a broad volume of the atmosphere, creating a diffuse explosion rather than a point impact. This process explains the wide area of radial treefall and why no single, large crater was formed. It's a complex dance of physics, transforming a solid, or icy, body into a massive, destructive pressure wave. Nearly 105 years after Tunguska, another celestial visitor provided a modern, sobering analog. On February 15, 2013, a meteor streaked across the sky over Chelyabinsk, Russia, exploding in an airburst with an estimated energy yield of 500 kilotons of TNT. Though significantly smaller than Tunguska, the Chelyabinsk event was captured by countless cameras, offering invaluable real-world data on airburst phenomena. The shockwave shattered windows in thousands of buildings, injuring over 1,500 people. It served as a stark reminder that such events are not merely historical footnotes but ongoing threats, bringing the abstract science of cosmic impacts into immediate, human focus. The Chelyabinsk event offered critical insights by vividly demonstrating key aspects of the Tunguska mystery. Both were atmospheric airbursts, generating powerful shockwaves that caused widespread damage without creating impact craters. However, the scale was vastly different. Tunguska's energy release was roughly 30 to 40 times greater than Chelyabinsk's. While Chelyabinsk produced numerous fragments that were recovered, the lack of significant remnants at Tunguska further supports the idea of a less dense, more volatile object, like a comet. The parallels, though, underscore the universal physics of such cosmic encounters and the ongoing vulnerability of our planet. Over the years, the Tunguska event has attracted its share of more exotic, even fantastical, theories. One such idea posited that a microscopic black hole passed through Earth. Such an object, theoretically, would create entry and exit holes on opposite sides of the planet, causing massive disruption. However, no evidence of an exit hole has ever been found on the other side of the Earth, nor have the expected seismic or geological signatures materialized. This theory, while intriguing from a theoretical physics standpoint, remains firmly in the realm of speculation, lacking any empirical support in the context of the Tunguska observations. Another imaginative theory proposed that the Tunguska explosion was caused by a fragment of antimatter annihilating with matter upon entry into Earth's atmosphere. The complete conversion of mass to energy in an antimatter-matter reaction would certainly explain the lack of physical remnants, as the object would simply vanish in a burst of gamma rays. However, the energy required would necessitate a vast amount of antimatter, far beyond what is believed to exist in the observable universe in such concentrations. Furthermore, the distinctive gamma-ray signature of such an event was not recorded by any instruments, rendering this theory highly improbable, despite its appealing solution to the missing object. Perhaps the most popular, and least scientific, alternative theory attributes the Tunguska event to an alien spacecraft. Proponents suggest a UFO malfunctioned, exploded, or even deliberately crashed to avert a greater catastrophe. This theory, fueled by the mystery and the absence of clear answers, captures the public imagination. However, like other fringe theories, it lacks any credible scientific evidence. No wreckage, no discernible alien technology, no unique energy signatures beyond a conventional airburst have ever been found. While intriguing, the alien hypothesis remains firmly in the realm of science fiction, far removed from the rigorous scientific inquiry that continues to define Tunguska research. Today, scientists continue to investigate the Tunguska event using an array of sophisticated tools unavailable to Kulik. Remote sensing, including satellite imagery, allows for detailed mapping of the blast zone and subtle changes in the landscape. Advanced computer modeling and simulations recreate the atmospheric entry and detonation of various objects, testing different hypotheses against observed data. Geophysical surveys employ ground-penetrating radar and seismic techniques to probe beneath the surface for anomalies. This technological revolution has not only refined our understanding but also demonstrated the enduring scientific relevance of this unique historical cosmic impact, proving its mystery is far from solved. A more recent point of contention in Tunguska research revolves around Lake Checo, a small, circular lake located about 8 kilometers northwest of the blast's epicenter. In 2007, Italian scientists proposed that Lake Checo might be a genuine impact crater lake, formed by a fragment of the Tunguska object. Using sonar, they identified an anomaly beneath the lakebed that resembled a buried object. However, subsequent core sampling and carbon dating of lake sediments have largely indicated that Lake Checo is much older than 1908, suggesting a natural geological origin. While the debate continues, the current scientific consensus leans away from it being the primary impact site. Studies of surviving trees in the Tunguska blast zone have revealed interesting biological anomalies. Many large trees that survived the immediate shockwave exhibited accelerated growth in the years following 1908, marked by unusually wide growth rings. Initially, some attributed this to the fertilizing effect of blast debris or even radiation-induced mutations. However, more recent ecological analyses suggest that this accelerated growth is likely a result of the reduced competition for sunlight and nutrients in the devastated forest. With vast numbers of trees flattened, the survivors had abundant resources, leading to a natural and vigorous regeneration response, a testament to nature's resilience. Beyond its scientific intrigue, the Tunguska event serves as a stark warning and a critical turning point in our understanding of planetary defense. It underscored Earth's vulnerability to impacts from near-Earth objects, or NEOs, which can cause significant devastation even without striking the ground. Tunguska highlighted the urgent need for comprehensive asteroid detection and tracking programs, prompting global efforts to identify and monitor potential cosmic threats. It galvanized scientists and space agencies to develop strategies for deflecting or mitigating such objects, transforming a Siberian mystery into a driving force behind humanity's efforts to protect our planet. Despite a century of research, the Tunguska event continues to hold some of its secrets. While the airburst hypothesis is widely accepted, the precise nature of the object, whether it was a stony asteroid or an icy comet, remains a subject of debate. Its exact size, composition, and trajectory are still debated by scientists, each new study adding another layer of complexity or clarity. This enduring fascination is a testament to the scientific spirit, the persistent drive to understand the unknown, to piece together clues from the past, and to push the boundaries of human knowledge against the backdrop of an incomprehensibly vast cosmos. The mystery persists, inviting further inquiry. The Tunguska event is far more than an isolated historical incident, it is a pivotal moment in planetary science. It fundamentally reshaped our understanding of atmospheric entry events and the destructive potential of cosmic objects. Before Tunguska, such events were largely theoretical or relegated to geological deep time. Afterward, it became clear that Earth faces immediate and tangible threats from space. It highlighted our planet's vulnerability and inspired a new era of space exploration focused on understanding and mitigating these risks. It stands as a unique case study, pushing the boundaries of scientific inquiry and reminding us of our cosmic neighborhood. Today, over a century later, the Tunguska blast zone remains a site of scientific interest and a quiet memorial to the power of nature. While no grand monuments mark the precise epicenter, the regrowing forest itself is a living testament. Nature, in its persistent cycle, has begun to reclaim the devastated land, with young larches now rising amidst the skeletal remains of their fallen predecessors. The area is largely protected, a natural laboratory where the long-term ecological impacts of a massive airburst continue to be studied. It stands as a silent, vast testament to an invisible force that forever etched its story into the Siberian landscape. The Tunguska Event serves as a profound reminder of cosmic chance. Had the object arrived just a few hours later, the Earth's rotation would have placed a major European city, or even Moscow, directly in its path, leading to an unimaginable human catastrophe. The event underscores the fact that such impacts, while rare, are an inherent part of our planet's cosmic existence. It is not a question of if another significant impactor will strike, but when. This awareness fuels the ongoing vigilance of astronomers and planetary scientists, constantly monitoring the skies, striving to ensure that humanity is never again taken by such a powerful, and potentially devastating, surprise. Ultimately, the Tunguska Event is a powerful testament to the beauty and challenge of scientific inquiry. It began as an incomprehensible phenomenon, an unexplained devastation in a forgotten corner of the world. Through decades of tenacious exploration, meticulous data collection, and innovative theoretical work, scientists have transformed it into a cornerstone of planetary science. The enduring mystery, the questions that still linger, only add to its allure, reminding us that the universe is vast and full of wonders, both terrifying and awe-inspiring. It proves that the most compelling stories are often found where the known ends and the unknown begins, inviting endless exploration.